So we'll continue. So continuing with this introductory lectures on quantum criticality. So today we'll talk about Landau-Ginzburg-Wilson theory. Okay, so what have we done so far? So we've been talking about the 1+1 dimensional quantum Ising model, transverse field Ising model, and we looked at Kramers-Wannier duality. Then we worked up to an exact solution of the d = 1 transverse field Ising model. So that's nice. We were able to pinpoint exactly the position of the critical point, look at the spectrum, extract critical exponents, at least some of them, and others can be obtained as well. But of course, we're not only interested in physics in one dimension, one spatial dimension, we're also interested in higher dimensions. And so although we have this exact solution in 1+1D, this transverse field Ising model does not admit, at least so far, exact solutions in either 2+1 dimensions or 3+1 dimensions. And so how do we proceed? Okay, kind of generally speaking, if we don't have an exact solution, then what do we do? Does it mean we can do nothing? Of course not. We can do other things, and of course they will be approximate, but they can also allow us to, in principle, access critical properties. And so one framework that we can use is so-called Landau-Ginzburg-Wilson theory. So instead of trying to solve directly the lattice Hamiltonian, we're going to be interested only in a coarse-grained description, what plays a central role, at least for symmetry breaking transitions, which is all I will be talking about these lectures. So it's a coarse-grained description in terms of the quantity called the order parameter. So what's the idea? So Alex showed us this nice little picture, and this is second slide of snapshot of the Ising model. So let's see, we're in 2+1 dimensions. So classically, let's say first classically, and then we'll think about quantum problems. So I'll have some lattice with a bunch of spins. Okay, that if I look at a snapshot, they will have a particular pattern. Just one more row here. Okay, and so that would be the model on the lattice. But what I'll do is, instead of working with a lattice with the original lattice degrees of freedom, microscopic degrees of freedom, I will do some sort of coarse graining. Okay, so I'll pick some position. Okay, so what I'll do is I'll basically average over a cluster of spins of a certain size. The center with respect to some origin of that cluster will be denoted by some continuous position R, and I'll define a sort of coarse-grained order parameter that will be, will have a continuous position index. Okay, where what I'll do is, instead of working with the lattice spin, I will average over all these lattice spins that are contained in this region. Okay, so summing over suitably normalized, but it doesn't really matter that much. We'll be averaging over all the spins that are located in some sort of mesoscopic region. Okay, centered at R. Okay, you can think of this as some sort of sliding average of these spins, and I say mesoscopic because I want to average over more than just a lattice spacing, but I don't want this region to be the whole system size. So there's a bit of a hierarchy of sizes. So it's a little bit crowded here. Let me just erase this part. Okay, so what I'll have is essentially the dimension roughly of that region will be a length scale that I'll call lambda inverse, and so that will be sort of bigger than the lattice spacing, but much less than the system size. Okay, so this is system size, this sort of macro scale, and this is the lattice constant spacing, which is our microscopic scale. And the idea is that And if I do this and I choose these things well enough, then instead of having some discrete, Z2 variable, this is going to become a real valued, a kind of continuously varying quantity. Okay, and one rarely actually does that in practice, but of course, there's these early coarse graining Kadanoff real space RG methods, but so to prove rigorously that this is going to be a smooth function, we may have to do a bit more work, but at least conceptually, it seems to make sense that you will have some smoothly varying function. Okay, so I go from this discrete variable to some sort of soft spin real variable that will be my local order parameter, and this quantity lambda that I will define in such a way that lambda is a inverse length scale. So I'll call this a kind of UV. So the idea, I want to go from a lattice model to some continuum description. So let's say for a classical system, then the partition function would be, okay, so first on the lattice, I just sum over all possible spin configurations. So product over all sites, and then for each site, sum over the two possible values of the spin. And then, the classical Boltzmann weight, some Hamiltonian, which is a function of these Ising spins. So this is a sum over microscopic configurations. This is the sort of exact partition function, discrete set of configurations. And then the idea is that instead of working with this exact representation, I will be trading this for a sort of functional average over all possible smooth configurations of this coarse-grained order parameter. There will be some Boltzmann weight that now will be not a function of these discrete variables, but a functional of these continuously varying configurations. Okay, and yeah.
Is there a reason why now you're doing classical?
Yeah, I'll write down the quantum. So it's just that now these configurations, they only vary in space, but in the quantum problem, of course, they also vary in imaginary time. So, I'll just add the tau in real time or imaginary time. Yeah, but this is statistical average. This is a partition. Then, the hope is that we can capture the right physics, at least the universal critical physics, by working with these continuum statistical field theories. Okay, where these sort of coarse grain in this problem, magnetic textures, which are continuous. All right, and so as William is saying, so we're really interested in quantum systems in these lectures. So in quantum systems, the configurations will evolve in real time or imaginary time for partition functions. We have them evolve at imaginary time. So that means that my partition function in this coarse grain representation will be some functional integral over this coarse grain order parameter that depends on position, but also on this imaginary time tau. And so this functional of m of r and tau is what we call the Landau-Ginzburg-Wilson action, or functional. Okay, so all right, so so it's a very non-trivial problem to try to compute what this S is going to be from first principles, right? So we, as I said, this coarse graining procedure is not really something we actually do. It's more of a sort of conceptual procedure, so we do not typically derive it, and so we will rely on sort of general principles to constrain the form of this action. And so the form of S of this Landau-Ginzburg-Wilson functional is fixed by a number of things, some assumptions. So there'll be a requirement of locality. So as we said, we start from some local lattice Hamiltonians, and so we expect that the resulting coarse-grained action, again, if we choose this mesoscopic length scale to be, not too large, should also be a local action. We would have symmetries. So we certainly want to preserve the exact symmetries of the lattice problem. Okay, so in this case, the symmetry will be this Z2 symmetry that sends sigma I Z to sigma minus sigma I Z. So of course, this order parameter, coarse-grained order parameter, which is an average of the sigma I Zs. If I flip all the sigma I Zs, I flip the M as well. So that will be a symmetry under M goes to minus M of this action S. And then also analyticity, okay, which is maybe a little bit harder to prove, but the argument here is that from the central limit theorem, we expect that there will be some probability distribution that sort of let's say nearly Gaussian, and then with some corrections. Okay, so and with these constraints in mind, we can attempt to write down functional and see what we get. Okay, there's other ways we can do this. We can also start from the, let's say in the classical problem, we can start from the lattice problem, and then at least we can expand this effective action and sort of derive something, but here I want to be a little bit more general and just work from these conditions. Okay, so from these general conditions, then an action we'll write down will be, okay, first of all, we'll assume it can be written as the integral of some local density. Okay, so this is my, so that's one of the aspects of the constraint of locality. So we'll be integrating some local function, which will be a function of this order parameter, but also in general of its derivatives, right? So we expect the free energy to depend on the value of the function at every point, but also on how quickly those things vary, both in space and in time. So we expect it should be a function of m and its derivatives, both in time and spatial gradients. And so we'll call this Landau-Ginzburg-Wilson Lagrangian. Is it really a Lagrangian density, but we often omit this word. And there's a sense in which we do not, it's not meaningful to have, for example, to be integrating over length scales that are less than this cutoff. And so I'll denote this by this sort of notation here where, and that'll be important later on when we talk about renormalization group transformations, but there's a sense in which, this in real space, there's some cutoff distances should be greater than this inverse cutoff, and in the momentum space, momenta should only go up to lambda roughly. So that's the action, and then the Lagrangian itself will again be constrained by these assumptions. So locality will mean that we expect again that this will only involve the function and its derivatives up to certain powers of these things. For example, some time derivative term, some spatial derivative term, and then powers of these functions of the order parameter. And of course, I want to enforce this asymmetry constraint. Okay, so I can only have even powers of m and its derivatives, and and there's many more terms we could write down. Again, note that these couplings, C, K, etc., they're really all phenomenological coefficients. We're not, again, attempting to relate them precisely to the lattice coefficients, even though, as we'll see, the position of the critical point, for example, will be dependent on, as we'll see, this parameter R, and so this, could be related to the lattice coupling G, at least in some way. Okay, and so we'll be writing down this action. This is in general, let's say at some finite temperature and for a system of a given size. But we're interested in quantum critical phenomena. So at 0 temperature corresponds to beta goes to infinity, and in the thermodynamic limit, which means system size goes to infinity, then we really have a quantum field theory, Euclidean in d+1 dimension. So I'll denote by a capital D the space-time dimension. Okay, so in a sense, we engineer things such that we would arrive at a quantum field theory because we want to use quantum field theory tools to study criticality. Okay, so the question is, how do we use this action? So we converted an intractable lattice problem to an intractable quantum field theory, interacting quantum field theory. So how does that help us make progress? So we'll be describing the quantum phase transition in 2 steps, essentially mean field, the mean field approximation, and then we'll add fluctuations to that. Okay, so what's the mean field approximation? Well, we have a functional integral. We're just going to do a saddle point evaluation of this functional integral. Okay, so that's what the mean field approximation means in this sort of path integral treatment. Okay, and so what that means is that we start from this, infinite dimensional functional integral, and we approximate it by evaluating this path integral at the minimum of this action. Okay, so we can find some configuration M naught that minimizes this action S, then that's a first approximation to the path integral. So we'll demand that we'll try to find the extrema of this action. Okay, and furthermore, we have to think whether that's a reasonable choice, but we'll assume that we'll be looking for a saddle point that is spatially. Okay, and this is where we want to make sure that we define our order parameter in a meaningful way. So for a ferromagnetic transition, then certainly if the spins are all aligned in the same direction, then this coarse grain order parameter will be uniform. If we had an antiferromagnetic transition, then of course we would want to define our order parameter in such a way that we get something that is uniform. So we would incorporate the wave vector of the order, right, and the definition of the good. So and so if we assume that the order parameter is uniform, then this functional is very simple to evaluate it, because these integrals over some for space-time of this Lagrangian density, all the derivative terms disappear because we look at a constant order parameter configuration, and this is just a multiplication by the space-time volume of the sort of potential part of our Lana-Ginzburg Lagrangian. Now this functional derivative is just a ordinary derivative. So if I minimize this, then I get 2 different values. So that's the standard potential. So if R is greater than 0, the minimum is at 0. And so this is the symmetric phase, the order parameter vanishes. And if R is negative, then we have this Mexican hat potential or double well potential, and we minimize the action with a non-zero expectation value. Okay, plus minus. And this is the broken phase. So at the very least, we've discovered something very simple, which is that there is a transition in this R, is essentially should be proportional to G minus GC, because at least near GC, because this is exactly where we thought this transition G greater than 1 is fermagnetic, G less than 1 is fermagnetic. Okay, so we have our this B happening here. Okay, so mean field is very simple. It's not telling us a whole lot. And so we'd like to go a bit beyond that. We'd like to know some critical exponents. And so we'd like to look at fluctuations. Okay, we could already find some exponents here. For example, the beta exponent, how does the order parameter grow with the coupling? It's already there. It's 1/2. But let's turn to fluctuations. Okay, so of course we made a big approximation. We replaced, all these spatially and time varying order parameter configurations by a constant. So there are fluctuations that depend on space and time that we should reintegrate, but we'll make this fluctuation approximation, which is that we'll assume that phi is much less than m0. Okay, of course, in the symmetric phase, then phi is m, but the idea is that we'll be treating these fluctuations to Gaussian order only, at least initially. So that's what I'm going to write here. So we'll do a Gaussian approximation to our path integral. So we'll expand this action to order, to quadratic order in the fluctuations and see what we get. So, so it's simple. We look at all the terms in our action. So the gradient is the gradient of phi, the gradient of the time derivative of m, the time derivative, and then we have these potential terms. So this becomes m naught plus 2 m naught phi plus phi squared. The term is m naught 4 plus 4 m naught cubed phi plus 6 m naught squared phi squared. Okay, plus terms of higher order that we said we truncate at quadratic order. And therefore, the Gaussian action, okay, S is S0, which will be this sort of uniform piece here, plus fluctuations, okay, where S naught is just S evaluated at M naught, and delta S is a Gaussian action. This 1/2 dt 0 to beta ddr, and then we have C partial tau phi plus K gradient of phi squared, and then so this mass term, we have R, and then we have this U m0 squared over 2 phi squared. And again, we have these cubic terms in higher order, and we will neglect them because we're only working at Gaussian order for now. Okay. So that's a very simple theory. Solve it by going to momentum space, frequency momentum space. Okay, so Fourier space. So we'll expand our field, fluctuation field, in terms of discrete momenta and frequencies for, I'll keep beta and V finite for now, so sum over spatial momenta and sum over these Matsubara frequencies, e to the I q dot r minus omega n tau, and the Fourier components of the field phi of q I omega n. Okay, so I plug this in there, and this diagonalizes the action. So I get delta S 1/2 over q and I omega n of 5 minus q minus I omega n, and C omega n squared plus K q squared plus C inverse squared by q I omega n, where I define this C as follows in terms of these parameters in the coefficient of the phi squared term. So C is to be square root of K over R plus U m naught squared over 2. And this is in fact the correlation length. Okay, so here there's a unique correlation length that would be the longitudinal correlation length in general. Okay, and so R greater than 0, it goes like root K over R. And for K less than 0, it's K over minus 2R. Okay, there's a factor of root 2 difference, but having related our R to the G minus GC tuning parameter, then this tells us that the correlation length goes like G minus GC to the minus a half. Okay, so we do find, as expected, for a continuous transition, a divergence of the correlation length. And so this tells us that the new exponent, correlation length exponent in this Gaussian approximation is 1/2. Okay, so this predicts that nu is 1/2 in this Gaussian approximation. So already that differs a lot from exact result for the 1 plus 1D transverse-field Ising model, which was 1. Okay, for d equals 1 or capital D 1 plus 1 for the transverse-field Ising Hamiltonian. Okay, so that doesn't really inspire much confidence. There's a big disagreement if we look at d equals 2. So of course we want to ask ourselves, this Gaussian approximation, when is this valid? An uncontrolled approximation at this point, and if it's not valid, can we improve upon it? How can we go beyond it systematically? Is okay, what we want to ask ourselves. So let's look at the first question. This Gaussian approximation should be valid if the fluctuations are indeed small, right? So if they are not small, then there's no reason we can expand in those fluctuations. So we will consider the strength of these fluctuations. Okay, so to do that, we'll define a 2-point function for the order parameter that I'll call chi, some sort of susceptibility. So just the 2-point function of the fluctuations in frequency momentum space, so that we can just read it off from the Lagrangian. And so the propagator of the fluctuations. So it's 1 over c omega n squared plus k q squared plus c minus 2. Okay, so just free propagator. And so we would like to compute, the sort of variance of these fluctuations. And so this will be sort of equal time, same time and same position average. And so, equal time, equal position means integral over all q and omega n in Fourier space. So 1 over beta v, sum over I omega n and q of this chi of q and I omega n. And so again, recall that we're interested in the zero temperature limit. We're doing quantum phase transitions, and the thermodynamic limit v goes to infinity. So this discrete sum becomes an integral d omega over 2 pi, integral d dq 2 pi d of 1 over c omega squared plus k q squared plus c minus 2. So we can do this omega integral. So we get 1 over 2 root k c, and then integral d dq pi over d of 1 over root q squared plus c minus 2. We just care about how this will be some function of the correlation length. We just care about how this scales. So we have integral d q d minus 1 q squared plus c inverse. So you have essentially 1 power of q. These 2 powers of q cancel out. We have some momentum scale to the d minus 1. So basically this goes like c to the 1 minus d. Okay, so that's the strength of the fluctuations. We really need to compare the fluctuations to the magnitude of the order parameter squared. And so if we take the ratio, okay, so m naught itself we saw depends on the correlation length on the tuning parameter, like square root of r. Square goes like minus r, and so this goes like c to the minus 2. So if we take the ratio of the square of the fluctuations to the square of the order parameter, then we get c to the 3 minus d. So these here spatial dimension, and so we want to ask, if this stays small as we go near criticality, but this okay, does this remain much less than 1 as g goes to the critical g, which is when c goes to infinity? Well, it does only if this exponent is negative. Okay, so only if d is greater than 3. So this is what we'll call the upper critical dimension. This theory, so above d equals 3, then these fluctuations are under control. The Gaussian approximation is valid, but if d is less than 3, then these fluctuations blow up. Okay, so the Gaussian approximation, we do not expect that it will be valid. And indeed, clearly it does not work. Certainly not in 1 plus 1 dimension, but also not in 2 plus 1 dimension. So if d is less than this upper critical dimension, dc plus, which here is 3, we need to go beyond the Gaussian approximation. Okay.
And what's your thing for d equals 3?
Then it's Gaussian with logarithmic corrections. Yeah, that's right. Yeah, because you would have some sort of log divergence of c exactly at d equals 3. So then how do we go beyond this? And so that's the story of within this Landau-Ginzburg-Wilson approach of the renormalization group and the epsilon expansion. So I'll start that and then we'll finish this afternoon. So what's the idea here? We want to use a bit of intuition to devise a strategy to go beyond this. So at the quantum phase transition, we saw that this correlation length diverges. Again, that was mentioned by Alex. And so that means that everything, these correlations extend over all possible length scales. And okay, so these fluctuations are correlated on all length scales. Okay, so if the theory doesn't have a length scale, then there's some scale invariance. Okay, so there should be some self similarity or scale invariance in physical properties. And in particular, this means that our Landau-Ginzburg-Wilson partition function, in a sense, shouldn't depend on the choice of size of our mesoscopic region. Okay, it should be invariant exactly at the transition under a change of this coarse graining scale. And so we'll look at an increase, let's say, of the coarse graining scale. In a sense, we can only do an increase because we're losing information as we coarse grain. So that's why I know this renormalization group is really a semi-group. It's not a group. And so will be an increase of this scale from lambda inverse here, looking at it, coarse graining scales, so thinking about first in real space, we'll be increasing it by some factor b, where b will be greater than 1. Okay, so right, so we'll try to exploit that idea, turn that into a calculational tool to compute critical properties. For simplicity, it makes sort of less writing. We'll rescale in our Landau-Ginzburg-Wilson action both space and time and also the couplings, so as to make our action have Lorentz invariance. Okay, so we certainly can do this here. Give us some velocity parameter. Then, in a sense, we are we're fixing, and so we'll write this action in this space-time form, derivative partial mu over space and time indices, and then we have these various couplings, so on and so forth. And okay, so we'll do that again. So x now will denote space time coordinates, r and t. Capital D's, we said this is p plus 1, and this I'll call this, these first two terms, I'll call this S naught, this is a purely Gaussian piece. And then here, in addition to working with this space-time formulation, I will also apply an isotropic cutoff in space and time. Okay, so we really started with a cutoff in space. Modulo certain assumptions, when you coarse grain in space, you also get a smooth function in time. And we might as well apply an isotropic cutoff that makes computations easier. Okay, so then we'll apply an isotropic cutoff in space and time. So this is something we can do for these types of problems. If you think about problems of metallic quantum criticality, for example, where you have a Fermi surface, this becomes very different. But here we're squarely in the realm of relativistic quantum field theories. Okay, and so yeah, that's right, because we're interested in computing thermodynamic properties on this partition function, right? So we're naturally arriving at a Euclidean action. Of course, you can continue back to real time if you'd like and have a Minkowski action, but here we're interested in thermodynamics variant. Yes, that's right, because this is a space-time derivative. Yeah. Yes, questions? Yeah, that's right. You can do the computation. There's no problem actually with for these problems with working with especially when we go to momentum space. You'll see, we'll be basically doing integrals over some space-time momentum that are bounded by this cutoff lambda. But you can do these computations. You don't have to do this. It's akin to a slightly different choice of cutoff, but you will get the same universal result. So you can also have really work with these computations like this, where now this will be sort of unbounded, and this will be bounded only for the spatial momentum. For example, as we'll get to that, but the coefficients in your beta function might be slightly different, but the position of the fixed point might be slightly different, but the exponents you get will be the same. Yeah. So the universal physics is okay. So really, what this cutoff means is that I can express this in momentum space. So when I do this momentum space decomposition of the order parameters, again, if we're now on, I will be using these space-time coordinates. Really, what this means is that I truncate the theory to only contain Fourier components up to some cutoff lambda. Or again, Q without an arrow means vector Q and also frequency. So that's the cutoff. It's a theory that's defined with a cutoff. And so what we want to do is change the coarse graining scale and demand that the partition function remains the same if we're at a critical point. So okay, so just pictorially, the way you can picture that in your mind is if we coarse grain from a real space lattice constant lambda inverse to a slightly bigger one, then you can imagine that I could take a snapshot of my order parameter. It could have some sort of fluctuations like this, and I have these fluctuations on this side before I change the corresponding scale of lengths of order down to lambda inverse, and then if I change the corresponding scale, that amounts to eliminating Fourier components, the high momentum Fourier components, and so I'm getting rid of the Fourier components that are between lambda and lambda over b. So it's in a sense you're sort of smoothing out, you're removing these fast wiggles, and you're keeping, let's say, the slow wiggles, which are on a length scale of order of b times lambda inverse, and we're going to keep doing that actually. So this was Wilson's idea to do this systematically, was so again precisely to work in momentum space. Okay, so he said, well, let's take this Fourier decomposition and we'll split it up into a sum of two terms. So we'll divide our order parameter m of x into two pieces, m lesser of x plus m greater of x, where m lesser of x denotes the Fourier modes we want to keep, which are the ones that are with momenta less than lambda over b. So we'll call these the slow modes or slow fields, and then m greater is the remaining modes with momenta in between lambda over b and lambda and lambda. Okay, so ddq. Okay, so these are the fast modes. Okay, and furthermore, his idea was to say, well, we'll consider a very slight increase of the coarse graining scale, and so we'll actually consider this b to be very close to 1. Okay, so we'll consider this b 1 plus a very small number plus an infinitesimal that I'll call dl. Okay, and therefore, this set of momenta here now, becomes a very thin shell. Okay, let's see, if you're in 3 dimensions, then that's a very thin shell with inner radius lambda over b, which is much less, slightly less than lambda, and then outer shell lambda. This is a very thin shell of thickness, lambda minus lambda over b, which for infinitesimal dl, this is approximately lambda times dl. So if dl is small, this is a thin shell. Okay, so all right, so I think this might be a good stopping point where okay, so the next step will be to implement these transformations, and the fact that I use this notation dl is suggestive that I'll be trying to perform these transformations, compose these infinitesimal transformations, and then derive some differential flow equations. So there's 3 steps. We first will integrate out these fast modes, derive an effective theory for the slow modes, and then rescale everything such that the theory for the slow modes looks the same as the original theory, but with different couplings. And then we'll see how these couplings flow as we coarse grain more and more. Again, these will give us the RG flow equations for this 5-4 theory. Okay, so I think stop here. Any questions?
What allows, you comment on in which situations our Landau-Ginzburg theory is going to be Lorentz invariant? Is it because the technical frequency is 1?
Yeah.
What else? What changes?
That's right. So there's different ways in which it can, be non-Lorentz invariant. So you might start from, let's say, some Ising model, for example, where let's say we look at the classical case, or it doesn't really matter, quantum case as well, where you have exchange couplings that are different in the x direction and the y direction, right? So you might coarse grainier theory, then you would expect that, for example, instead of having some gradient of m, you might have something like, some coupling kx dxm plus some different coupling, something like this. So, so that would be some theory that has some anisotropy. So it's not Lorentz invariant. There's other possibilities, but something like this, what will often happen is that, you'll start with your sort of bare theory or UV theory that is not Lorentz invariant, but very often you flow to a fixed point where, these couplings will flow to one another. And so in the renormalized theory, the fixed point will have an emergent Lorentz symmetry. So, it's obviously on the lattice, there's no Lorentz invariance already at this very simple, theory we wrote down. On the square lattice, if you have the same exchange coupling, like you wouldn't even write that because, the microscopic lattice Hamiltonian has some discrete rotation symmetry that would be violated by this. You wouldn't even write that. It's already, if you only keep these couplings at, quadratic order, you already have Lorentz invariance, right? Okay, so that's one situation. Of course, there can be more severe violations of Lorentz invariance. So if you have a theory where, for example, a theory with fermions where, your fermionic degrees of freedom, instead of having some linear dispersion, they have something like, like a quadratic crossing, something like that, right? So this theory has some dynamic equals 1 and 2. So you wouldn't even start with a Lorentz invariant theory, and that would likely persist down to the sort of infrared physics. So we don't always get Lorentz invariance. It's certainly never there at the microscopic level. In many cases, it is emergent at the fixed point, but definitely not always. For sure, if we have, for example, metallic quantum critical points like Sung-Sikli was talking about, then yeah, we never get a Lorentz invariant theory.
For this case of C=2, can you still do RG about the same?
That's right. That's right. So in many of these problems, the basic idea is, you have to ask yourself, what's the locus of points at low energy, right? So if it's a problem like this where, it's a semi-metal, right, where, your chemical potential is here, and so all the low energy physics is near a point, then, these scale transformation will do, they all kind of generalize quite nicely to these problems. If the locus of point, right, because then the idea is that you will have some, some shells of momenta, and then you're sort of approaching this low energy point, everything works. If you have a theory where the low energy degrees of freedom are on a Fermi surface, then clearly that's not a very sensible thing to do. You want to keep all these degrees of freedom. So you want, for example, you would have to define a sort of cutoff region that is like an annulus, for example, around this Fermi surface. And it's a very different type of scaling. So you can still do scaling for sure. It doesn't mean you cannot do RG, but so the same basic ideas apply, but the technical details could be very different. So, yeah.
I have slightly tangential question about low range invariance. It's kind of thermal systems. So some 2 points in an equilibrium space-time, which are distant, can have zero Minkowski for the main big.
In Minkowski space, right.
So then can that be a problem when we do this transformation from Minkowski's space-time theory to a equilibrium space-time theory?
I'm only aware that these RG transformations is typically something one does for Euclidean quantum field theories, and typically you're interested in the low energy physics, so you interrogate the theory, you do this RG, you find some fixed point, and then once you've determined the fixed point, then you can compute dynamics. You can look at the Minkowski description of all that. I don't really. Yeah, so you work in imaginary time. That's correct. So I'm not aware that you really would want to do RG in real time. I'm not quite sure what that would mean, unless you had some non-equilibrium phenomena or something like that. So, but for this, we're interested in systems in thermodynamic equilibrium, and so these are fixed points of Euclidean quantum field theories. Yes, I don't think this creates any issues because we work in this Euclidean Riemannian signature. Yes, question.
If they actually NPY,
Right.
then the flow to a point where there is already.
Yeah, it depends on the interactions as well. But typically what you'll do, you can define a sum and difference of these terms with a coupling that will be kx plus ky over 2, kx minus ky over 2, and very often what you'll find is that this difference coupling becomes some irrelevant coupling and it disappears. Yeah, so I guess it will depend on so often what happens is that you will have, for example, one thing I have in mind is problems where you have, for example, fermions and bosons, for example. So you might start with a theory where maybe a better example is a slightly different one. So you might have a theory where the fermions are relativistic, but this is the case for some of these gross number theories, right? So you have fermions that have some dispersion with some velocity, so that by itself is Lorentz invariant, and then you will have some scalar field where I guess I need to have a c squared here. Oh, c squared, yeah, so it's like this with a bosonic field that also has some Lorentz invariant theory, but with a different velocity. Okay, so the theory globally does not have Lorentz invariance. So if they remain uncoupled, sure, you will never have Lorentz invariance. But what often happens is that if you have some Yukawa interaction with some coupling G, you might couple, for example, the boson field to some fermionic bilinear, and that that would, for example, describe some transition in some Dirac semi-metal with interaction, for example. And so what will happen is that you'll find that when the two fields are decoupled, these velocities remain distinct. I guess I didn't write this quite correctly, right? This is really gamma 0 delta t plus some cf gamma I delta I, something like that, right? That's what I meant to write. So, but you'll find that due to the coupling between these two fields, then the beta function for these velocities are such that they will flow to some common fixed point, right? So what you'll find is that if you look at the flow of the velocities under this parameter L that we'll look at in more detail, so you'll have, for example, some curve for the renormalized fermion velocity and a curve for the renormalized boson velocity, and they will start at different Bayer values, but then they will flow to some common value in the infrared. And then the resulting theory has Lorentz invariance with some new kind of emergent, velocity C star. So that's a very common occurrence. So it's not to say that this always happens, but right. So I think likewise, if you have, for example, fermions with an isotropic dispersion, but the bosons have an isotropic dispersion, then I believe that the fixed point is isotropic. But okay, one needs to look at the model, right? It's not a general statement. Any other questions?
There was a question on.
Oh, in the chat. Oh, I should look at that. Good. Thank you. Can you expand on the point about the central limit theorem and demanding analysis of the action? Right. So I think here the idea is that, right. So one would like to, for example, yeah, I don't know that I can say that much, but right. So the idea was that we wanted to, we had some microscopic description, let's say, for some classical problem, right? As I said, so we would sum over these microscopic configurations, and then we want to find some effective action, right? Some sort of measure like this. So you're trying to ask yourself, right? How can I represent this, this partition sum by a sum of these Boltzmann weights, right? And yeah, so in a sense, you're sort of trying to ask yourself when a representation of this type becomes valid, and okay, so that's one thing, and then the other thing is that you want to ask yourself, how will this depend on this this variable here, and yeah, so I think one needs to, yeah, I'm forgetting the precise statement here, but yeah, so we're summing over some number of random variables, inside this mesoscopic region. And if that is sort of large enough, then this action here will have sort of analytic properties. Yeah, but I can't say that I remember the precise statements where you can sort of rigorously show that this is analytic. Yeah, so this is discussed a little bit in the statistical field theory book by Carter, but I can't quite remember the details of the arguments. Yeah, it's not a formal proof, it's just a statement. Maybe others know in the audience. Yeah, it's often an assumption that we write down. I think certainly the fact that we have local interactions is something that matters. But beyond that, I can't.
The classical is but is there an element in the operator sense that if you added an operator?
I don't know. I think even these statements, right? So this was in the context of a classical statistical mechanics. I think we often accept that it kind of carries through. In the quantum case, it gives results that are reasonable. So, yeah, I mean, you typically get non-analytic contributions to a Landau-Ginzburg action when you start from an action that has degrees of freedom, especially light degrees of freedom or gapless degrees of freedom, and then you integrate them out, and this can generate non-analytic contributions to the effective action. So, one can try to work with that. Sometimes it works, other cases it doesn't, and then we often try to work with actions that contain all the light degrees of freedom, right? We don't want to integrate them out. We want to really treat them on equal footing. And then usually in these cases, at least for physical microscopic Hamiltonians, then I'm not aware that there's examples where you have a physical microscopic system that has a transition that is described by some sort of non-analytic Ginzburg-Wilson action. Again, unless you've integrated out gapless degrees of freedom, right? For example, like in the problem of metallic quantum criticality, you can work with an order parameter coupled to a Fermi surface. You integrate out these gapless fermions, and then you will get, terms in your effective action that will have some non-analytic dependence on the frequency, right? So that's the Hertz-Millis framework, and it gets you somewhere, but it's not in higher dimensions. For example, it works well. In 2 dimensions, you can get some things qualitatively wrong. So, or it's not a complete theory. So, yeah. So, anything else? I think there's no more questions, right? This was Rufus's question. Okay, so I guess we'll stop here and we'll resume in the afternoon.